Well, everyone who's here is here. Yeah. Oh, wait. That's true. Okay. Raise your hand if you connect to Wi-Fi using Eduroam in here. Okay, and ours only works through Illinois Net, right? Yeah, Lecture Helper just works through Illinois Net. Okay, so that could be part of it too. Bunch of little things.
So make sure, tell me, or like, if you want to use it today, it is on, then you have to do it.
All right, so I want to start because it's Friday, and the sooner we start, the sooner we get done, and then it's the weekend. So at the very end of last time, we kind of tied a bow around BTrees, and where I wanted to start today was by reminding you that BTrees were an implementation of a dictionary, and we're not done talking about implementations of a dictionary. In fact, we're going to branch off in two different directions. Our first additional dictionary implementation has to do with data that is so big that it cannot fit in main memory. The structure that we're going to use for this implementation is a B tree, and at the end of the discussion, I think you'll want to know, well, gosh, BTrees seems so useful. Don't we use it for other things too? And the answer to that will be yes, in fact. But for now, the way to think of BTrees is as a dictionary for big data in the real big data sense. The sense that it no longer can be handled just by the memory that exists next to the processor in your very own laptop. Okay. So the answer here, so we're still talking about dictionaries, and I'll just remind you very quickly that in dictionaries we have these functions which are insert, remove, and find, or search, and let's see, what was I going to say? And those are the things that we're going to use to evaluate the effectiveness of our dictionary data structure. Oh, and furthermore, though, they are functions that operate on key value pairs. So our data looks like a unique key or identifier together with a bunch of data associated with that key. And let's see, and those things constitute what we're trying to put in our dictionary or what we're trying to store. All right, but all of my examples for ever since we were doing linked lists, all of the examples that we see in class only show the keys. Everything we do assumes that the keys are obvious and the data is just somehow sitting behind those keys. And that will be true for BTrees as well. We're going to focus on the keys, but the data is still assumed to be there somewhere associated with those keys. Okay, so can we always fit data into main memory? We would not be having this conversation if we could. So because you're here today, the answer is no. And think about what that implies. How big is the RAM on your machine, on your own machine? 4 gig or 8 gig. So the question is are there data sets that we interpret as dictionaries that are bigger than that? And the answer is, well, sure, of course there are. Otherwise, that would be the kind of memory that we used all the time. So where do we keep the data? And the answer is, well, do you know what this is? Yeah, this is a hard drive. You know, an optical hard drive with a spinning disk, right? This is getting to be old technology now. So actually, many times we don't keep it there. We keep it, this is an old-fashioned hard drive. What do hard drives look like now? They're solid state drives, right? And I always draw those like that because to me, as somebody who works on algorithms and is very far from any kind of hardware, it's a black box. I guess I should color it in. It's a blue box, okay? So a solid state drive might be where we would store our data. And what that should imply to you is, oh, things are faster, right? If we store our data on solid state drives, we can get to our data faster. There's another really important place where we store our data if we can't store it right next to the processor in our machine. Where? Where might we store it? That's right, in the cloud. That's right. We're storing it off someplace else, and we don't know what they do with it, right? So what these three things have, the cloud. Pretty sure my dad thinks his data is sitting up there somewhere. Yeah. What these three things have in common is that they incur additional cost for getting our data. They incur additional time to actually get our data so that we can process it. Now, that's new for us in this class because for everything we've done so far, all of our analysis assumes that all of our computation is about the same amount of time. Moreover, it's a really small amount of time. We assume that evaluating a conditional takes about the same amount of time as deploying another function, which takes about the same amount of time as assigning a value to a variable. All those things we assume just kind of operate in the same amount of time, and that amount of time is really, really fast. But the problem now is that if all of our, and if our data fit here, then that assumption is okay. But now we're in a situation where our data is remote, and these operations take a long time. But communication, I'm going to generalize to the idea of communication across devices is slow. Okay? And so if we can't get at our data immediately, then we're going to be incurring some other costs, so we better start counting. Okay, well, how slow is slow? I think laptops, I check this slide every so often, but probably only once a year. And I think the last time I checked this slide, it still wasn't unreasonable that I was talking about a 2 gigahertz processor, okay? These things are being sped up in your laptops by having multiple processors, but nonetheless, a 2 gigahertz processor was not, not like a true dog a year ago, the last time I looked at this. Now, the question is, what does that mean? What does it mean for something to be a 2 gigahertz processor? Well, let me ask you this. What does that M stand for? What does the M stand for here in this sentence? Million is correct. So this is 2 million instructions per time unit. What's the time unit you think we're talking about here? Seconds? Oh, not seconds. Not minutes. That's the other way. Whoa. Not nanoseconds. I don't get to go that far. But it is millisecond. Okay, so it's 2 million instructions per millisecond. Now, these instructions are not the same thing as, I don't know how to get this right again. Hold on. There. Those instructions are not the same thing as the operations that we do in code. In fact, the operations that we do in code use a few of these instructions. And you'll learn about this in your architecture class or your classes that teach you how your code interacts with the actual machine, but not here. Suffice to say 2 million instructions is still many, 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 many comparison operators. It isn't quite 2 million, but it's many comparison operators on the same order of magnitude, okay? For example. All right, so we've got these super fast machines. These super fast machines, they can do a lot of work very, very quickly. All right, but in contrast, for a hard drive, and you know, like I said, I looked last year, so last year that was still relatively current, to get one piece of data or to find a piece of data on a hard drive took about 6 milliseconds. Okay? Now, so that means to get your, that quantifies, it illustrates the orders of magnitude difference between how long it takes to get your data versus how fast your machine is at doing anything with your data. Now, you might say, oh, come on, solid state drives are so much faster, but last time I looked, that figure related to solid state drives was only a factor of 3 faster. So, yes, it gets you a bit, and you feel it, but still, if your data is remote, it takes you a long time to get it, especially relative to computation speed. Okay, so let's ask for a moment if this is ever relevant to us. If this is, I mean, maybe all the data that we would ever want to compute on does fit in memory. So imagine an AVL tree that we're going to build on US driving records. Okay, so how many of them are there ever? How many driving records are there ever? 2? No, there are more than 2. 2 what? 3? There are more than 3. How many driving records do you, well, what's the population of the United States? About 350 million or so. So that's how many there are right now. Maybe half of those people drive. And if you think of the history of cars in this country, then maybe, I don't know. Anybody want to offer a number? Yeah? What'd you say? All right, I'll go with 700 million. Anybody think that's unreasonable? 700 million driving records? I'm going to write it like that. Why not? Okay, how big is a driving record? How big is a driving record? Has your picture. Oh. What do you think? What's a safe bet? How big? What's the biggest one? It's a safe bet here. Okay, fine. I'm just going to say 5 meg. Anybody think that's crazy? So how much data do we have total for US driving records? Oh my gosh, right? It's going to be, oh my, 3.5 whats? It's like 3,500 gigabytes, right? So, or 3.5, wait, oh no, I'm just not going to, million gigabytes. There we go. Or 1,000 terabytes. Or 3.5 petabytes. Is that how it goes? I don't know. I'm pretty sure some order of magnitude bigger than the RAM that's in my machine, right? So I'm safe in saying that it's 3.5 million gig. Yeah. So I don't know about you. Maybe you can get a better machine than I can, but I don't have that much RAM in my machine. Okay, fine. Now let's assume for a second that our model of our dictionary is an AVL tree. What I want to know is how tall is that AVL tree? How tall is the AVL tree? How am I going to figure that out? What are you going to do? Talk to the person next to you and come up with some answer. If I take these 700 million records, if I take these 700 million records and I build an AVL tree out of them, how tall is the AVL tree? That's all I want to know. base it on all of the results that you've seen so far for bounds on heights of AVL trees. I'll give you a hint that the first thing I did in thinking about this was divide in half. Anybody have an estimate? Seriously. What do you think? Do you have an estimate? Are you raising your... What? Yeah, log base 2 of, and what is that? Yeah. Yeah? Yeah, about 50 or 30 or whatever deep. 50 is safe, right? 50 seems like a small enough number. I guarantee you there are no more than 50, okay? No more than 50. When I was doing this exercise, I said that was 30, right? And I was thinking, okay, no more than 30. But no more than 50 is still definitely true. You can fit a lot of data into an AVL tree of height 50. And you know what? If all of our memory fit in RAM, that would be awesome. It means the number of comparisons for all our dictionary functions, you know, they only take 50. The height is only 50. No big deal, right? But here's the problem. Here's the problem. So let's pretend like this is our AVL tree, okay? And it contains all of the records. So first I want to do a little aside. Is this an AVL tree? Is it? Okay, I want somebody to volunteer a key that I could insert so as to make it an AVL tree. What key could I insert into the structure to make it an AVL tree? 42 will work, yep. Okay, so I'm going to go ahead and do that because I want to talk about AVL trees for a minute. So I'm going to insert 42, and now this satisfies the balance characteristics of an AVL tree. Okay, so now here's what I'm going to assume. I'm going to assume that I have already loaded the root into memory. Okay, I already have the root node for comparison. And what I'm going to try to do is determine whether 66 is in the tree. Okay? So what do? You know this already. You compare 38 and 66, and you go, hey, 66 is bigger. It must be in 38's right subtree. Now, if the tree lives near the processor, if you've got it close to you, you don't think about what you have to do next. But in this context, it may be that 38's right subtree, whose root is 51, so I'm going to do it like this, that when I have to go get 38's right subtree, it involves taking a walk out to the hard drive, spinning up that hard drive, bringing the right address, picking up the data, 51, there's 51, and walking it all the way back to the processor, where a very quick comparison is done between 51 and 66, and we determine that we should go get 51's right subtree, right? You don't want me to do that walk, right? You'll fall asleep. You will take a nap in the time it would take me to go get the next value that I need to compare against. The orders of magnitude that we're talking about here are significant in similar ways. Now, I haven't thought carefully about the pace of my speech versus the pace of my walking. But the orders of magnitude that we're talking about are significant in terms of the communication cost with the hard drive. So this is a bad idea. This storing the nodes of our AVL tree on disk So we could go get them when we need them is a bad idea. And in fact, it's not the disk part of it that is a problem. It's actually the AVL tree that's a problem. The format of the AVL tree, the structure of the AVL tree. So I kind of lied to you. Because when I took my trip all the way out to the drive and I picked up value 51 from it, I didn't just get the key for 51. I got 51 together with all of its neighbors. In fact, I got an entire block of data. Now, what that means on this picture, I should have walked with it. What that means on this picture is in contiguous memory, probably in contiguous memory, in a file, the file that contained 51, when the processor asks for that data, it automatically gets not just the value that we're looking for, but an entire block from the disk, okay? Now, that suggests to me that we should be smart about how we store our data. And it suggests, in particular, that if we're using a tree-based structure, we should keep the tree very shallow. And secondly, we should make sure that all the data we bring back from disk in a node, or I'm sorry, in a search is relevant in a block. Make sure all the data in a block that starts with B, that stands for BTree, is relevant. Okay? All right, so those two, of course, are related to one another. If every trip out to the, if every level of your tree induces a disk seek, then you can minimize the number of disk seeks by making sure everything you bring back is useful to you. Okay, so let's switch gears for just a second. I have a question for you. What is that thing up there? Tell me everything you can about the data structure that's on the, yeah, it's an array. It's a sorted array. That's right, it's a sorted array. Well, that's sort of an incomplete answer because what it really is a BTree node. And this particular one is a BTree node for a BTree of order 9 or more. Okay, so a BTree node for BTree of order 9 or more. Okay, that's part of a story to be continued. We'll talk about that more in a minute. Okay, so now what's implied by this is that we are going to do disk seeks, and every disk seek is going to bring us a node but in our tree. But now this time our node contains more data. Okay, so in fact there's correspondence between the block and the node. Okay, the block of data is the data contained in a node. Okay, so we want to minimize the number of disk reads from a disk, build a tree, the disk block. Yes, nodes will have more than one key. Trees should be balanced and shallow. In practice, branching factors, or, oh, we don't even know what that means yet. So maybe we should, rather than me describe these things to you, I think I should show you one. Could you close your eyes for just a second? I want to get a good one before you open your eyes. Okay, so close your eyes for just a second. I'm going to reload this page maybe many times. I was going to ask if somebody in the room had reading glasses, but you probably don't. How do I reload this page? I need to reload. Oh, it's not. Oh, I want a new one. sorry. I want a random one. I don't want this particular one. I've been playing with it. You can open your eyes. Sorry. Okay. That one's not a bee tree. Oh, wonder what's going on there. Okay. Here's what's cool about this. Oh, I like this one. I like this one a lot. Okay. So this is a bee tree. Take a look at it for a second and make sure you understand, or at least build your own understanding of what's going on here and how it's structured. Some questions you might ask yourself are, how many children are there for each node? And the way I'm going to ask you to show me that you understand what the structure of this thing is I'm going to ask, if I were to insert value 500, where would it go? If I were to insert value 500 into this structure, where would it go? Okay, so first let's talk about the structure of it. Anybody want to describe the structure and your observations? What do you see here? What's interesting about this? Daniel? Okay, leaf nodes have 2 numbers or 3. Okay, so I think what you're telling me is every node has more than one key. They look like B tree nodes, right? And they're sorted, yeah? Good. The number of values in each node is, I'm going to say this, the number of keys in each node, look, I can do this better, is 1 less than its number of children. So the number of keys in this node is 2, and that's 1 less than its number of children. And that's true for everything that isn't a leaf node. So that's an excellent observation. That goes hand in hand with what you observed as well, right? Okay, yeah? Yeah, okay, so there's more than one. And you're noticing something kind of special about these. There's a range of values that are kind of valid. What range of values are valid here? What's valid for putting in here? Anything less than 186, right? What's valid for putting in here? Anything between is key here. That word between comes up a lot in discussing this data structure. All the keys in this node, in the child node, are between the keys adjacent to it, right? And all of the keys in this node are at the end. They're greater than anything here, okay? All right, so now, where does 500 go then? Where does 500 go? And I think I want to do this actively. I want somebody to come up and point to where 500 goes. And there's a cup of coffee on it. So the first person to touch the front of the screen, I will buy a cup of coffee. Oh man, front row, incentive. Okay, where does it go? Show me. It's the... Yeah, okay, really good. Okay, you win. You have to send me an email to remind me. Okay, thank you very much. All right, so he said 500 goes here. Now, this whole finger pointing thing is a little bit arbitrary because we don't know exactly what he meant by that, except that he observed that 500 is greater than 431, so it must go somewhere in its right B tree. 500 is less than 556, so it must go somewhere in its leftmost tree, subtree. 500 is greater than 453, so it must go somewhere in its child. Oh no, there isn't a child. Uh-oh. I don't know what we should do. So let's try it and see what we should do, what happens. Okay, so we're going to insert 500 into this structure. I can make this a little bit bigger so you can see it in the back row. All right. Next, oh, it's just as we predicted. Oh, look. 500 fits in that node. So we did not have to make a new node, and so we did not have to increase the height of the tree, right? That's kind of cool. All right, any questions about that? Okay, yeah? Oh, when do we get a new child? I'm going to tell you an answer that's a big tease, okay? Never. We never get a new child. All right, I'm going to show you something. Okay, so first of all, I'll tell you that this is a B tree of order 5, which bounds the number of keys in each node. So each of these nodes can hold up to and including 4 nodes, okay? So let's insert, what do you want to insert? What experiment would you like to have at this point? I think I want to insert 217. Is that all right with you? All right. Goes right here, right? Are you happy with that? Okay, let's see. Let's see if the system's happy with that. Insert. Next. 217 goes into, gosh, this one. Uh-oh. There's a problem. So here's what we do. We split the node on the median value. Okay, so the median value is important. And we throw up the median value. I think of these things as vomit trees. We have guests here. I shouldn't be saying vomit in front of our guests. Right? So these trees, unlike the trees you've seen before, they grow upward instead of downward. Okay? All right. So let's see. What's another interesting value to insert? I'm going to play with things over here a little bit. I'm going to insert, let's see, 582. Oh. And I'm going to do this, try to do this kind of quickly. Insert, next, 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 no surprises. And then I'm going to insert 583. Next, next, oops, next, next, next. What's going to happen? 583 gets thrown up. Okay? Yeah, you like it? I'm going to insert one more for you, 475. Insert. Next, next, next. No surprises. Somebody volunteer a key that they would like to see inserted into this tree. Neil, you're done today. Yeah? 476. Dun, dun, dun. Are you ready? Do you have a question before I do this or a different key to suggest? Yeah, this is an order 5 tree, which means 4 is the maximum number you can. Oh, in the tree itself? No, and we'll talk about that. So it's a keen observation. All right, so everybody in this room is dying. What'd you say? 476. Insert. Dun, dun, dun. I should have music that goes along with this. So look at this. 476's journey is interesting, right? Because it came down and then it gets thrown up. But, uh-oh, now what? All we know is that a new node, a new key has come to play in a node for which there is no room. The algorithm says split and throw up. I wanted to make a joke like Friday nights, but no, I'm not going to. I'm not going to do that. All right. Any question about it? I think you should have questions, especially, I think you already have this question. The question that was asked was, wait a minute, if each of these nodes can contain only 4, and we can't grow going down, are these fixed size trees? Do they contain only a fixed number of nodes? We would not be spending so much time on this if that were the case. So what happens? What happens when we throw up from here and we fill up the root? What do you think happens? Describe it out loud. You did exactly the right sign language. Describe it out loud. Yeah? You do the same thing. You split and throw up. So this tree grows going up. Does that make sense? Okay. The sign language is ambiguous. Okay, so I'm going to draw a picture. Are there any other questions? Yes. Excuse me? Yes. When that root node reaches 5, I think I probably shouldn't go through that process because it would take us a long time to fill that thing to 5, right? Okay, so when that root node reaches 5, it will split and throw up. So the tree will grow up. Does that make sense? Yeah, the height increases, and that's what increases the height. That's right. That's exactly what increases the height. It's the only thing that increases the height, and it doesn't happen very often. Okay, I have a few little things to say. Oh, lab BTree will be next week. It is our hardest lab. Okay, it's the most time-consuming. It's made by the same, it was designed by the same person who designed LabDict. Yes, so I'm just warning you ahead of time that ultimately it's a worthwhile exercise. I hope you felt that way about LabDict, but you may want to budget a little bit extra time. In the past, we have actually given extra credit for it because it incurs so much extra time. So I'm a little apologetic. Yeah? So that's a perfect question. So the question is, how do you construct this tree from the beginning? And actually, I think that's a good time for me to go back to my slides, because I think I can draw pictures of that outside of the applet. Okay, so the question is, how do we start this thing? How do we start this thing off? Well, as you can see here, I have drawn for you an empty B tree. When you insert your first node, it's going to go there, okay? Now, the actual orchestration of this on disk, that is what your file containing this data looks like on disk, is a matter of study in the databases class. That's where they cover this work, how you lay out your data in the files. For this class, it's most important just kind of to know that this thing exists, okay? So when you put your data into the first B tree node, it is put somewhere on disk in a file with a particular format. Okay, our interface lets me stop there. When you insert another node, it will go in its correct place in that same file. When you insert another node, it will go in its correct place in that file. When you insert another node, same story. And I'm talking about a B tree of order 5, just like our previous example. When you finally insert that 5th node, what happens is that file that contains all of this data will undergo a reformatting that is not the subject of this course. The model for what happens, that is the drawing of our B tree, afterward will look like this. We're going to split on the median and grow up a tree. Okay, so here's the median. I'll put a little M there, and here's the left, and here's the right. Okay, any question about that? And understanding it at this level is adequate. Our interface in the BTrees lab is a little artificial, so I'm not going to talk about either how it's actually done in much detail or how it's done in the BTree labs in detail here. You'll have time to puzzle that out. All right, any question about it? Did I answer your question? Okay. All right, anything else? Yeah? So the question is, if we're taking the median, is the order of our tree usually odd? And the answer is, nah, we would just take one or the other. Maybe we'd switch between them. It doesn't really matter very much. Okay, so we have looked at these things, and we kind of have this instinctive understanding of how they work. I want to go over a more formal definition of them for just a few moments. Now, I looked for a long time for a definition that I liked, and as with any other data structure, there are a lot of very simple minor twists on the definitions. This one ultimately captures, I think, most of the things that we observe that we have observed so far. There's one critical point that I want to bring up in the end. So, as we said, for an internal node, and by internal node I mean non-leaf nodes, the number of keys are the number of children minus 1. Okay, so that relationship is captured in the definition. All the leaves are on the same level, which means that a search for same level designation simply says this is a very nicely balanced, in some sense, tree. Okay, all leaves hold no more than m-1 keys. Okay, so that's the order, the bound the order places on the number of nodes. The size of those keys, the m, is related to the architecture of your machine and its unit of transfer between the processor and the disk. So as technology changes, m is going to change. So we're just going to leave it be m. All non-root internal nodes, so everything between, or everything here, have between m/2 and m children. Now, think about what this says. It means that those mid-level nodes, and this actually applies to the leaves too in a slightly different way, those mid-level nodes are at least half full, and no more than full, right? They're at least half full. This is an artifact of the splitting, because think what happens when these things fill up. We divide them in half. We never shrink them to something tinier. And then after we divide them in half, we're always growing them by giving them new data, by throwing data up the tree, right? So the only time when we shrink a node is only by dividing it by half, and we don't make it any smaller than that. The only node for which this is a different story is, of course, the root, because it might have only one thing. All right, any question about that? So now the implication of that is that these nodes are, in a sense, efficient. That is, there's never going to be a big node that only has one key in it. That would be a waste of space and a waste of a seek. We're saying, look, every node can be this big, and we guarantee that it's going to be at least this big. That is, we're going to get a lot of keys for our search. Okay, so the implication here is all nodes except the root are at least about half full. It's actually half minus 1. Okay, they're at least half minus 1 full. All right, so that's good news. The root could be a leaf or have between 2 and m children, that is between 1 and m minus 1 keys. And the keys in a node are ordered. You already knew that. All right, any questions about it? Okay, so this is kind of cool. So that's the definition. My question is, based on that explanation of this thing, what's the order of this tree? I made a tree for you. It was a little present. What's its order? What do you think? At least 5. Can you do better? Good, it's true. I believe that because there's a node there with 4 keys. Can you be tighter than that? 5, or can it be 7? No, because you know what? These guys don't have enough keys in them. If it were 7, we would be guaranteed that these nodes would have at least 3 keys in them. Okay, so it can't be 7. How come it can't be 6, though? It can't be 6, I'll tell you that. How come? Why can't it be 6? What about this tree makes it impossible that for this one to have been 6? And the way to think about this is, what would the shape of this tree look like if 6 were the number of keys? If 6 were the order. Anybody see it? It's very subtle. Yeah? So if it were 6, the internal nodes would have to have at least 3 children, which implies 2 keys. So that's that minus 1. It's actually a minus 1 for the number of keys. So in an order 6 tree, you could actually have 2 here. But there's something else kind of subtle. Yeah? Yeah, maybe, but we might have inserted something more over here that made it different, made them the same again. I'm going to go over here, and yes? Because the root? Yes. What about the root? So here's the thing. If this were an order 6 tree, we can take that many keys per node, right? And so all of these would still be in the same node. They wouldn't have been divided out. That is, we would not have split and thrown up the root. Okay? All right, any question about that? So I can look at this tree and see that it's an order 5 tree. Six would allow these to be in one node. So 6 isn't right. Okay, right? An order 6 tree would let all those 6 be in the same. It would have 6, look. An order 6 tree would allow for 6 children. 1, 2, 3, 4, 5, 6, right? Okay, any questions about it? No, 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 we're not done. We're not. Oh. He left the party early. Okay, I'm going to show you some pseudocode for finding a key in this structure. And I promise you right now, pieces of this code will bug you, but I want you to figure out what you think I'm talking about, okay? I want you to get in touch with your inner analyst and tell me what about this code is annoying. And in this code, I'm going to search for the value. I'm going to use this pseudocode to do a BTree search, BTree search on this tree, whatever it is, for value from the root, we'll say, for value 13. Okay? Yeah, how about 37? I'm going to look for 37. I like that one better. For value 37. All right, so what does this code say to do? That while loop is just basically figuring out if 37 isn't in the current node, which subtree does it have to be in? Okay, and we're just incrementing. We're counting the number of subtrees that we're essentially walking over. That's what that while loop does. So it says, while we're not at the end, and while the key that I'm looking for is bigger than the key in the node, keep going. That is, increment where this thing might be found. Okay? When that one ends, I tells you which child you need, unless the keys are the same, in which case you return true. If you are at a leaf, so this is a moment where this is truly pseudocode. I haven't really even described the interface to you. I'm just going to use the English. If we're at a leaf and we haven't found the tree, then we're going to return false. I really don't like this code because it could be this, right? There. In fact, it could be, yeah, all right. Otherwise, we're going to keep looking for it. Where are we going to look for it? Well, we're going to go get on disk this subtree, the ith subtree. We're going to go get on disk the ith subtree. So this is something we're going to assume exists. It's going to be where this function spends most of its time, right? And then we're going to continue our search with a recursive call to BTree search with the new thing that we found, the new data that we found, and the key that we're looking for. Okay, so what of this code bugs you? Yeah? Excellent point. Oh! Look at this. This while loop is just this while loop is a linear search, right? Our nodes are ordered. We could do binary search to figure out where to go. But guess what? Neither one of those determines the running time. The thing that causes all of the running time in this is this disk read. That thing is orders of magnitude more. That thing is orders of magnitude more than anything else this code is doing. In fact, we can consider M, or the number of nodes in this thing, to be a constant, so that traversing that number of nodes can be considered to be a constant. So, but you are right. I'll write it down for you anyway, that we could do binary search here. But that's sort of like driving to California to save $50, 50 cents on, I don't know, a car or something, right? Like it's spending something to gain not very much. Okay, I think that's all I have. Wait, oh, you guys are so sweet.